All right, so we're going to continue. In particular, all these functions, these vector-valued functions that we've seen, certainly have to do with motion, and I think I mentioned that. And in this section, we're going to concentrate on finding the velocity and the acceleration, right? And so we're going to think about this r of t, this vector-valued function, as the position of some object in space, right? Or in this case, in the plane, but you can easily add a z component to this if you want, right? Right. So we're thinking about this as the position vector here, right? So as time moves along, right, the position vector will change. And in particular, we have the position vector here at some time t0, let's say. And we can also find the position vector, let me do it in red, at some time later. How about t0 plus delta t? So delta t is just some short time later. So some short time later, it got moved to this position over here. So this will be r of t0 plus delta t, right? And we can take the difference of those two vectors, right? So we can take r of t0, well, let's do it over here. So r evaluated at t0 minus delta t, or sorry, plus delta t, right? Minus r evaluated at t0. Right. So that, yeah, you can see where this is going, right? So that vector will be this here. So maybe I should give this a name, right? Let's call this delta r. Right? So it's a small change in the position. Right? And of course, right, we're just going to divide this by delta t. So this is the change in position divided by the change in time, right? This is our velocity. Well, specifically, it's the average velocity, right, from time t0 to time, let's say t1, which is t0 plus delta t again, right? Right. So, right, if you're dividing by delta t, if delta t is small, then think about what you're doing. You're making this vector longer, right? You're dividing by a small number, you're multiplying by a bigger number, right? Right. So that's the average velocity, right? If we want the instantaneous velocity, so I'm running out of colors here. I guess I'm going to continue to use blue here. The instantaneous velocity would just be the derivative, right? So you take the limit as delta t approaches 0 of r of t naught plus delta t minus r of t naught divided by delta t, right? And this is what we've been calling dr over dt, or r prime of t. Well, particularly r prime of t naught, right? So this is going to be evaluated at t is equal to t0. So it's the derivative at a particular moment in time, right? So, yeah, so what you can imagine doing is making this delta t shorter and shorter, and that brings this vector closer and closer. So now that I've completely messed up that picture, you can see what's going to happen here. If this is the curve, right, and we have our position vector, let's say this is the origin at a given time, right, then the derivative will simply point in the direction of the curve, right? So the derivative will point in this direction here. Not quite. There we go. That's better, right? So that's going to be the derivative of r at time t0. Right. And since this is, right, since r is the position function, right, the derivative of r is the velocity function. So this gives us the velocity at time t0. Right? So, yes, so velocity is just the derivative of position. Right? And that just comes from Calc 1. But now, of course, position is no longer a number, a scalar, it's a vector. Right? So you take your r, take the derivative, and this gives you the velocity as a function of time. I'm going to squeeze in the of t here. Oh, let me just start over, right? So v of t is the derivative of r with respect to t, or r prime of t. Right. So this is the velocity as a vector. Right. So velocity also has a direction. And it should be clear that it's just the direction of the curve. Right? If you use a different t, like let's say we find the position at this value of t here, let's just say a maybe, right? Then the velocity will point in this direction. So this might be v in terms of a, right? V is at time t equals a. Right. Yeah, so in general, when you have your position, right, traced out as a curve, all your velocity vectors will point along the curve. Right. Right. So these are all tangents to the curve. Right. And so the velocity vector is a good example of a tangent vector. If you want to find a tangent vector, just find the velocity, right? Find the derivative of the position. So velocity is just a specific example of a tangent vector. But if you want to find any tangent vector, just find the velocity vector, right? By just taking the derivative. Okay, makes sense? All right, so if that's velocity, how do you find the acceleration? So I'll call that a of t. So I shouldn't have called this scalar a here, but too late now. So this a is a time, not an acceleration. Just be careful of that. Well, it's pretty clear. You should remember acceleration as just the derivative of the velocity. And that's going to be true here as well. So officially, of course, you just take the limit as delta t goes to 0 of v of t plus delta t minus v of t, all divided by delta t. Right. And so what happens here, of course, is that as you get closer and closer, these velocity vectors get closer and closer. So the difference between them obviously gets smaller, but it might point in, let's say, this direction here. And maybe that might not be clear from the picture, but generally speaking, the acceleration as a vector, right, will point in some direction that probably is not the same as the velocity vector, although it could be. Right? So yeah, if the blue is the velocity, then the yellow might be the acceleration. Okay. So that's the acceleration, and of course it's also a vector. It has a position, it has a length, a norm, a magnitude, and a direction. Okay? Or of course you can think of the acceleration as the second derivative of the position. Right? Or r double prime of t. So that's a good example of taking the second derivative of a function. You get the acceleration, right, as a vector. If r represents position, of course. Right. So just a very simple example. Okay, so we have the position function is given as this, right? So this is a three-component vector, so it's a vector in space. t cubed minus 3t, 4t squared, and cosine of 5t. Right, and we have t is greater than or equal to 0, so we're starting at t equals 0. But you can see that the domain of this is all real numbers, but let's not consider negative numbers for t. Let's not go backwards in time, in other words. So this is the position of some particle at time t. Find its velocity and its, oh, sorry, not position, acceleration. So find the velocity and the acceleration at time t, at any given time. Right. So we did this in the last video, right? If you want to find the velocity, you just take the derivative. And now we know how to take the derivative. You just take the derivative of each component separately. So we get 3t squared minus 3, 8 times t, and then negative 5 times sine of 5t. Right? So that's the velocity. Right? And if you want the velocity at a specific time, say time t equals 7 seconds, then you just plug in 7 for t. I don't know why I picked 7 here, but So it's, let's see, 49 times 3 is 147. 147 minus 3 is 144. 8 times 7, 56. And then, well, whatever this is, negative 5 times sine of 35. Right? Not 35 degrees, right? 35 radians. Right? So I have no idea what that is, but it's some number, right? Yeah, you might want to double check my arithmetic here, but I think that's correct. Yeah. So that's the velocity, right? Acceleration, of course, is now just take the derivative again, right? So you're going to get 6 times t, 8, and then, let's see, negative 5 times 5 is negative 25 times the cosine of 5t. Cosine of 5t. And if you want the acceleration at time t equals 7, well, 6 times 7, 42. Then you get 8 for the y component. And then you get negative 25 times the cosine of 35, whatever that is, right? Okay, so that's all it is in this case. Velocity is a vector, acceleration is a vector. And we should talk about speed. The speed of an object, right? So the speed of the particle is just the magnitude of the velocity, or the norm of the velocity, right? So in component form, it's, v1 squared plus v2 squared plus v3 squared, right? And then take the square root, right? So you can do that here. If you want the the magnitude of the velocity, you get the speed, right? Okay. Yeah. Oh, well, okay. So while we're at it, what's the speed at time t equals 7? So you can say v of 7, or the norm of the vector v at 7, and it's going to be some really outrageous number here. So we get 144 squared plus 56 squared plus, and then whatever number this is, negative 5 sine of 35 squared, and then take the square root of that. So using my calculator, I get 8,064, approximately. Yeah, so it looks like it's the square root of 65 million something. So about 8,064.000, right? So we'll round to the nearest whole number here, 8,064. And we never gave units, right? So it could be meters per second or miles per hour, right? Yeah, so remember, speed is a number. It's a scalar. Right? So speed is the scalar. Velocity is the vector. So that's why we just get a number here. It's right. Speed is a number, scalar. Okay. So a good example for all this is projectile motion. Right? A projectile, you know what that is, right? Something you throw, or something that's launched. So you throw something, it goes up, and of course it comes back down. And by now you all know that the trajectory, that's the path that a projectile takes, this is called the trajectory, right, is a parabola. Or I should say, is approximately a parabola. It's not exactly, but it's close. Or, put another way, if there was no air, right, then the trajectory would be a parabola. I should also say approximately as well, but a very good approximation, right? But because we have air resistance, typically, right, it'll look a little more like this. And maybe that's an exaggeration, but, you know, right. So, yeah, so because, right, especially if you have a strong wind, it can blow it in all sorts of directions. I'm trying to get a good, yeah, so something more like this, maybe. Right, so that might be the true trajectory, but, so we're going to neglect air resistance, right? So if we neglect air resistance, we get exactly a parabola. And this is what you do in your basic physics course. Neglect air resistance. And, you know, depending on where you take it, who you take it with, they might talk about, you know, when you have air resistance, what happens, and you know, in drag forces and things like that. So air resistance, for example, is an example of a drag force. But we're not going to get into that here, right? So save that for your physics course, and they might get into a lot more details. And actually, if you make it all the way to differential equations, we will talk about drag forces and air resistance and viscous mediums in general. But yes, so in this we're neglecting air. There's no drag forces, right? So all there is gravity, right? All there is gravity, and gravity, of course, points straight down. And gravity, right, that's the acceleration due to gravity. We just give it the symbol g, right? And so we're going to use x and y here. We're assuming that the trajectory is in a plane, right, the xy plane. So this is planar motion. Obviously, if you have a wind, that could blow it, you know, left or right, so you might have a z component to the trajectory. But no, we're going to assume the simplest possible path, and that means it's in a plane, in the xy plane. So, yep, so this is g times j, although since it's down, it's going to be negative, right? Y points upward, and x points to the right. Right. So g is approximately 9.8 meters per second, or approximately 32 feet per second. Oh, sorry, per second squared. Oh gosh, that's Professor Guy would kill me if he saw me do that. Right? Not right. This is an acceleration. The units are meters per second squared, meters per second, right? And feet per second squared. Okay, good. Phew. So that's what g is in the two conventional units, right? Either 9.8 meters per second squared, 32 feet per second squared. It's all on your formula sheet. So if we know the acceleration, how do we get the velocity of this thing? Well, you just work backwards, right? Acceleration is the derivative of the velocity. That means the velocity is the derivative, is the antiderivative, or indefinite integral of the acceleration. Okay, and since the acceleration is a particularly simple vector here, you're just integrating negative g, which is a constant. Right? What do you get? You just get negative g times t, right, in the j direction. Right? However, don't forget, this is an indefinite integral. You also get a constant. Well, no, you don't. You don't get a constant number. You get a constant vector, right? Right. So what does that constant vector mean? Well, if you plug in t equals 0, well, you get negative g times 0, which is 0, plus c. So c as a vector is just your velocity at time t equals 0, or better yet, just v naught, v0, v sub 0. This is the initial velocity, right? Initial velocity as a vector. In other words, it's this vector here, the vector when you're first starting out. So that's how fast you're going and in what direction. It's your initial velocity. Okay, so yeah, let's make that official here. So v of t is just going to be negative g times t times the vector j, unit vector j, plus v0. Okay, so that's the velocity at any given time. So that tells you how fast you're going and in what direction you're traveling. Right. Now suppose you want to know where you are. Where is this thing? So that's the position. So how do you find the position vector? Given the velocity, right. Again, take another antiderivative or indefinite integral. So here we're getting negative g times t times the unit vector j plus another vector v0 with respect to time, of course. And if we do that, what do we get? We get negative 1/2 gt squared in the j direction, right? Plus v0 as a vector times t, plus another constant. Can we call it d? Right. So what is d? If you plug in, again, t equals 0, that's your starting time, you get 0 plus 0 plus d. You get d itself, right? So let's call that r sub 0 or r naught. This is your initial position. Right. And in this picture here, I just use 0 as the initial position because you're right. We're starting at 0, 0, which is the 0 vector. Well, no, it's a point. But, right, yeah, so we're splitting hairs here. It's a point that you can turn into the 0 vector with components 0 and 0. Okay, so that's your initial position, right? So you have your position function then. So it's negative 1/2 gt squared times the j vector, unit vector j, times v0 times t plus r0. Okay, so you have your position vector. You have your velocity vector. And of course you have what was given to us is the acceleration as a vector, right? Well, again, that's for projectile motion, right? The acceleration is just a constant negative g, neglecting air resistance and all that, right? So yeah, these are all on your formula sheet as well, so you don't have to memorize these, but you do have to know how to use them. So we will look at an example. Before we do that, I'm going to start over with these equations, but I'm going to write them in their component form to make it a little easier to visualize. Okay, so we're still talking about projectile motion, and at the top here I wrote the vectors that I just had before, but then I split them up into their components. Now, I know the book would not like this, right? Because typically they would write the components as v1 and v2 rather than vx and vy. So I'm going to do a little switch here and call them vx and vy as just the x component and y component. Okay, and I'm going to go back to the v1 and v2 later. But I think especially, in your physics courses and your engineering courses, you're probably going to see it like this, with an x and a y rather than a 1 and a 2. So I hope that's okay, at least for now. Right, and so these are, right, so these 3 equations really get split into 6 equations, right? Each equation has 2 components, right? And this is it. So be careful. When I write v0x, I mean the x component of v0, right? So v0 is also a vector. And it has two components, v0x and v0y. Right. However, let's suppose, right, so this might be my vector v0 here. However, let's also assume that we know the initial angle, the angle at which we're shooting this at, right? So we're shooting something, you know, up in the air at an angle theta. Okay, so something is launched with angle theta, right? At least initially, right? That angle will change as time passes. But so theta is the initial angle. Right, to the horizontal, of course. You could also take the angle to the vertical, but that's not the convention, right? So the angle is to the horizontal position. So in that sense, we know what v0x is, right? It's just v0 times the cosine of theta. And then v0y is v0 times the sine of theta, just by trigonometry, right? So, yeah, so we could have written it that way here. But again, it does depend on theta. So, all right, so those are the equations. Again, we're going to need those for the following example. Okay, so here's an exercise from the book. So it could very well be for homework. So again, one you might want to try on your own first. So you can pause the video, try it, and see what you get. Okay, so I'm going to see if I can work it out. At least I hope I can. So the question is this, right? So we have a baseball player at second base, throws a ball 90 feet to the player at first base. The ball is released at a point 5 feet above the ground with an initial speed of 50 miles per hour at an angle of 15 degrees above the horizontal. At what height does the player at first base catch the ball? Okay, so we have a lot going on here, right? So let's just draw the picture here. Here's the ground. Okay, so here's second base, and here's first base. Okay. And so we have the player over here, throws the ball at an angle of only 15 degrees, right? So not very steep. And then the player at at first base then catches it. And the question is, what's the height of the ball at the moment the player catches it at first base? Okay, so we know the initial angle is only 15 degrees. We know the initial speed. Right? In other words, the magnitude of the initial velocity, right, is 15 miles per hour. Oh, sorry, 50, not 15. That's the angle. Yes, 50 miles per hour. All right. And I think that's all we know. Oh, of course, we know the distance between second and first base is 90 feet. So that's the question. So how do we go about doing this? Well, we go back to these equations here, right? So we're looking for the height. That means we're essentially looking for the y component of the position, right? So here is the y component of the position. It's right here, right? So yeah, let's just write that down as something we need to find. Sorry, that was a sine theta, I think, right? V0 times sine theta times t, and then minus 1/2 gt squared. Okay, so we might as well plug in g. G is 32 feet per second. Sorry, 32 feet per second squared. 32. Right. Well, okay, that's maybe I'm jumping ahead of here, right? So this is g, and we know g is, right, 32 feet per second squared. Right, yeah, so we can plug in the numbers now. The initial height, I thought that was given, right? Oh yeah, 5 feet from above the ground. So this initial, right, so y0 is just 5 feet. Plus v0, v0 is 50 miles per hour. However, unfortunately, the distance to first base is not in miles, it's in feet. Right, so we have to be careful. If you use 50 times sine of 15 degrees times t, you're going to run into problems here because you're going to get different units. So before we do anything else, I think we should convert 50 miles per hour, right, to feet per second. So 1 mile is 5,280 feet. That's good to know. If you don't, just look it up, right? And 1 hour is 3,600 seconds. Again, that's 60 times 60. And so when you plug all that in your calculator, I get 73 1/3. I don't know what to do about the 1/3, but we'll leave it as 73 1/3 feet per second. Yeah, not great, right? But that's what it is. So 73 1/3 times the sine of 15 degrees. I'll do that on the next step, right? And then minus 1/2 g, that's going to be 16 feet per second squared times t squared. Okay, so if you multiply by the sine of 15, and again, make sure you're in degrees, 18.98. Approximately, so I think we better just write this as approximate. So y is going to be 5 plus 18.98 times t minus 16t squared. To be fair, all of this is approximate, right? G is not exactly, 32 feet per second squared. It's just a good approximation. So all of this is going to be approximate in the end anyways. All right, so now what do we need? We need to know the height, so we need the y value when the distance is 90 feet. So that's a problem because we need to know what t is, right? How long did it take? How long did the ball take to go that 90 feet? Right, so that's the problem with writing this as a function of time. We're not given that time. Right, so this is y of t. Yeah, so look, okay, let me just erase this and write it as y as a function of t. Right, so we're not done, right? We can't just plug in t if we don't know what that is. So the horizontal distance, that's the x is 90 feet, right? So if we can write x of t, that might be helpful. So first of all, this is going to be x0 plus v0 times the cosine of theta times t. Okay. So in this case, x0 is second base, but that's where we're starting at 0. So x0 is 0. Yep, so this is just x0 here. And v0 we know is not 50, but 73 1/3. So this will be 73 1/3 times the cosine of 15 degrees times t. All right, so 73 1/3 times the cosine of 15. I get 70.2 decimal places, so 83 times t. Okay, so that's the x components. I'll just copy it down here for posterity. So 70.83 times t, right, plus 0 because x0 is 0. Well, we want to know if the position is 90 feet, and that's at first base now, how long did it take to get there? So just divide by 70.83. So t is going to be approximately 90 divided by, 70.83. So it's going to be a little more than 1 second. It's approximately 1.27 seconds, sticking with the 2 decimal places. So the nearest hundredth of a second, probably close enough, right? Okay, well, guess what? Now we can answer the question because that's what we plug into y now, right? So y, evaluated at 1.27 seconds, will tell us the height at first base. Okay, so it's going to be 5 plus, sorry, that's a 5, not an S. I know my 5s sometimes look like S's. Sorry about that. Plus 18.98 times 1.27 minus 16 times 1.27 squared. Again, plug all that in your calculator. And I get 3.2982 feet, so we'll say about 3.30 feet. Right? So, yeah, so kind of a bad picture because, you know, I didn't know if it was going to be bigger than 5 feet or less than 5 feet. It turns out to be, you know, less than 5 feet. So roughly 3 1/3 feet, 3.3 feet. So that's all it is, right? Again, this is not the only way to solve the problem, of course, but this is, I think, using these equations, it feels like it's just the most direct way to do it. Okay, if you want another way, look at the next question after this. I think this is number 30 in the book. Again, in the 11th edition, this is number 30. So being an even number, probably not for homework after all, but a good problem anyway. So if you look at number 31, you could actually find the trajectory here as a function of x by eliminating t. So eliminating t as a variable from these two equations here, right? So these two equations here are in terms of t. If you solve for t and then plug that in here, you can write y as a function of x. And so that's number 31. I would encourage you to do that. Whether it was for homework or not, I don't remember. But it's a good exercise, a good exercise in a lot of algebra. So enjoy that. Okay, so here's one of my examples. We have a ball launched from the ground with an initial speed of 60 feet per second. Nice, because we don't have to convert, from miles per hour. Right? So 60 feet per second at an angle of 40 degrees to the horizontal, up a hill with a slope of 10 degrees. Right? So we have a hill that's sloping 10 degrees. What is the ball's range? Right? And that means how far up the hill does the ball land? Okay, so effectively, we're looking for this distance, right? From point A, which is where the ball was launched, right? We throw the ball, and essentially, how far do we have to walk to retrieve the ball? So what is that distance? I'll call it D for distance, maybe, right? So that's what we're looking for. Okay. So since the ball is launched from the ground, we might as well just call that position 0, 0, just to make it easy. So to answer the question, you can see what we need, right? We need the position of the ball where it lands, right? So that's going to have an x-coordinate, right, and a y-coordinate, right? Here's the x-coordinate, and then we'll pretend there's some y-coordinate over here. Right, and then of course D is just the distance formula, right, or the Pythagorean theorem, either way. So yeah, so the question is to find x and y, right? Where does the ball land? Is the real question here, right? So again, there are a couple ways of doing this, right? If you know the formula for the trajectory, as it, right, y is a function of x, which I just said that you could find that if you did number 31 in the book in the 11th edition. But I'm not going to assume you did it. I wish you would have done it, but if not, we could still answer the question by just using the same formulas we had for the position, right? So remember the x position is just going to be x0 plus v0 times cosine of theta times t, right? And then y is going to be y0 plus v0 times sine of theta times t minus, and then 1/2 gt squared. Since we know the velocity is in feet per second, we'll use the same half of 32, so 16t squared here. Right. And we're assuming that x0 is 0 and y0 is also 0 since it's from ground level, right? So that means x is really just, let's see, v0 is 60, and theta is this 40 degrees. Now be careful, it is 40 degrees to the horizontal, right? We're not measuring the angle from the hill, right? We're not measuring this angle, which is clearly 30 degrees, right? But that's not the angle we need here. We need the 40 degrees to the horizontal, right? So 60 times the cosine of 40 degrees times t. Well, you know what? I'm going to leave it exact for now. We'll get the approximations later. In the last example, we used approximations, which is fine. But let's see if we can get the exact answer here. If not, that's okay too. We'll round it, 2 decimal places is good enough. Okay. So y is going to be y0 is 0, right? And then we have 60 times the sine of 40 degrees times t minus 16t squared. Okay. Right. So again, we had the same problem in the last example. If we knew how long it took for the ball to go from point A to point B, I guess I'll call that point B. B is where it lands. You could say B for ball, but B for the landing point. So how long did that take? If we knew that, we have our x and y. So obviously, we don't have that. We don't know how long it took. That's not given in the problem. So we have to somehow find t. We have to somehow solve for t here. And again, if you eliminated t already by doing number 31, then this is a much easier problem because you just have to find your x and y, right? Right. But how to do that, right? So notice this yellow trajectory, that's the trajectory of the ball, right? Notice where it lands. It lands on the hill. And what's the hill? The hill is, we're assuming that the hill is just a flat, right? This is just a straight line. I mean, it doesn't say that, right? A hill could be curved, could be rounded, right? Could be this. But then that would make it an impossible problem. So we're assuming that the hill here is just a line. Right? And what's the equation of that line? Well, we know the slope of the line is 10 degrees, but that's an angle, right? Slope is rise over run, right? Opposite over adjacent. So the slope is really the tangent of 10 degrees, right? And so the equation of the hill is really just y equals m times x, right? Tangent of 10 degrees, whatever that is, times x, right? Plus 0 because, again, we're starting at 0, 0. So the y-intercept is 0. Okay, so how does that help here? Well, essentially, we just want to take the intersection, right? The ball lands where the trajectory intersects this line, the hill, right? And yeah, if you have the equation for y in terms of x from these two equations, then you just solve that system of equations. But the way I'm going to do it is a little more complicated because we did not eliminate t, right? We did not eliminate t, at least not yet, right? So on the other hand, we can do this, right? We can set the two y's equal to each other. So if we set the two equations for y equal to each other, because it's the same y at the point B where it lands, right? Right, because it's the point of intersection, I should say, between the curve and the line. So let's see what happens, right? We get 60 times sine of 40 degrees, and some of you probably already approximated that. That's okay. I prefer to get the exact. Minus 16t squared equals tangent of 10 degrees, right, times x. On the other hand, what's x? It's the first equation, right? So x is really 60 times the cosine of 40 degrees times t. So we've eliminated x, we've eliminated y, now we just have an equation in t by itself. So if we can solve that equation for t, then we have our answer. We just have to plug them back into the equations for x and y, and we have our location, we have our points, right? Okay, so how are we going to solve this? Well, notice we have a t squared, so this is a quadratic equation. Okay, so it's not just a linear equation. Let's see, so what should we do? Let's leave this on the left for now. So I'm going to do a lot of writing here. And on the right, we can simplify this a little bit. We have 60 times the tangent of 10 degrees times the cosine of 40 degrees. Okay, I don't know how to simplify that. We'll leave that as it is. And then maybe we can subtract this from both sides. Or why don't I bring everything on the left over on the right? So that'll become a positive 16t squared. Right, and this will equal 0, of course. So 0 equals 16t squared, right, plus 60 cosine 40 degrees, tangent of 10 degrees, and then minus 60 times the sine of 40 degrees, all times t, right? So I factored out the t here. Right? And notice that there's no constant term, there's no c here, right? It's ax squared plus bx plus c. Or in this case, it's at squared plus bt plus c. But c is 0, right? So this is a very simple equation to solve. Just factor out the t, and we get 16t minus, plus, let's see, 60 times this mess here. Cosine of 40 degrees, tangent of 10 degrees, minus the sine of 40 degrees. Right. And since that equals 0, well, we get two solutions. We either get t equals 0, or, let's see, t is going to be negative 60 times this mess here, right, all divided by 16. Right, and there you go, right? So that's the exact time. I think we can divide by 4, right? So this is negative 15 over 4. So, and we can distribute the negatives. So it's going to be positive 15 over 4 times the sine of 45 degrees minus the cosine of 40 degrees. Oh, 40 degrees. I don't know where I got the 45 from. So some of you are probably screaming, 45? Where's that? Stop. It's not 45. It's 40. Sorry about that. I got a little mixed up here. Yep, so there is no 45 degrees. It's 40 degrees. This is my terrible eraser. All right, there we go. Sine of 40 degrees minus the cosine of 40 degrees times the tangent of 10 degrees. Okay, so that's the exact time. All right, now we might as well just throw it all in a calculator and get the approximate time. Right, and so this is what I get, right? I get 15 over 4 times, so the stuff in parentheses is about 1/2. But let's be a little more precise. I'm rounding to 4 decimal places, so 0.5077. And so it takes about 1.9039 seconds for the ball to go this distance here, right, from point A to point B. Okay, so just under 2 seconds, right? All right, so now that we know what t is, we can plug those back into the equations for x and y up here, right? So I guess I'll do that down here. So x is going to be, see, I forgot already, 60 cosine 40 times t. So 60 cosine of 40 degrees, all times t. Now, again, I can plug this exact version of this in here, right, and get the exact answer. And I was going to do that. I don't know why I didn't do that. All right, so indulge me here. So this times sine of 40 minus the cosine of 40 times the tangent of 10 degrees. So I guess we get 225 times whatever this is. Sine of 40 degrees, cosine of 40 degrees, minus the cosine squared of 40 degrees times the tangent of 10 degrees. Right. Again, no point in really doing that unless you want the exact answer. So now throw it all in your calculator and let's see what we get. 87.5083, or roughly 87.5 feet. But again, I'll keep the 4 decimal places. Yeah, actually, if you calculate this, I get something slightly different. 87.5094, or 095 actually. Feet. So the 87.5083, that came from actually plugging in the 1.9039 seconds, and you can see that's a little bit off. But, you know, I think that's similar enough. All right, that's x, but notice we also need y. So that's going to be the second equation, 60 times the sine of 40 degrees times t minus 16t squared. Where t is what? Okay, so again, I think at this point, I'll just plug in this t in here. And it'll be close enough. Right, so y is approximately 15.4308. Again, your results may be a little bit different if you got the exact value, for example. This is also in feet, right? So the point B then, the point where it lands, has coordinates approximately 87.5 feet, but let's say 87.51. Now we'll go down to 2 decimal places, and 15.43. Okay, but the question was to find the distance, so that's the usual Pythagorean theorem, right? Distance formula. Okay. Well, looks like 88.86 feet. Okay, so that's how far we would have to walk to retrieve the ball. It's about 88.86 feet, so just under 90 feet, right? Or I should say just under 89 feet. But that's how to do it, right? Yeah, not an easy one, just one that you had to think about carefully here, go through the equations, and the key is to basically intersect, right, the line right with the curve. And these are the parametric equations of the curve. This is the geometric equation of the line, right? So yeah, we had to sort of play around with the three equations, eliminate t, and or actually solve for t first, and then plug those in to get x and y. On the other hand, if you had the equation of the parabola, y is a function of x, then you just intersect the two equations, and that will give you x and y, probably a little bit quicker than the way we did it. But either way, that should answer the question. And I guess I'll do one more example. Okay, so here's another example. And actually, I did steal this from the book. In the 11th edition, this is number 56. Right. So one of the later ones, and so probably not an easy one, but I don't know. I think it's pretty straightforward. So try it yourself and see what you get. So we're given that a particle travels along an elliptical path with position given by this position vector here, right? So, and they don't, do they say this? No, they don't. A and B are constants, of course. Right, so A and B are constant. And omega is the constant angular velocity, the constant angular speed. So omega is also a constant. And we want to find the velocity, the speed, and the acceleration. Right. So velocity, you know, is the derivative of the position. So that should not be hard. And it will be a function of time too, of course. So v is a function of t. Will just be r prime of t. So I think you can handle that. There's a chain rule here, so you multiply by omega. So this will be minus omega times a times the sine of omega t. And that's the I component, the x component, right? And then plus omega times b times the cosine of omega t, and that's the y component, or the j component, right? Okay. And, you know, you can factor out an omega. I think maybe we'll do that. Well, okay, we'll do that now, I guess. We don't have to, but why not? Times j. Okay, good. Right. The speed, of course, is just the magnitude of that vector. So speed, I guess we'll use v for speed, but it's the norm of the velocity vector. So that's just the usual square root, right? Now the omega factors out, but then you just get the square root of a squared times the sine squared of omega t plus b squared times cosine squared of omega t. Right. And of course, it would be nice to somehow factor out something so we get sine squared plus cosine squared. But we can't do that unless a and b happen to be equal, but they're not. In fact, you can see what happens. If a and b are equal, right, then it's a circle, right? Then that's just the radius. So yeah, a and b, of course, are just the semi-major and semi-minor axes of the ellipse, right? So right, this is an ellipse. We're set at the center here. I should probably use a different color for that. Right. So yeah, so A is the distance from the center to the vertex. B is the distance from the center to the covertex. And this is A. Yeah, so if A and B are equal, you just get a circle. Okay, because it's an ellipse, A and B are not equal here. Or at least that's the assumption. So unfortunately, this is the best we can do here for the speed. There's no way that I know of that we can simplify this. Okay, so yeah, this is the speed, and this is the velocity. And now we just need the acceleration. So for the acceleration, well, we have the speed, right? This is our v here. So just take the derivative of the speed. So we get another omega, right? We're going to get negative omega squared a times cosine of omega t times I. And then we're going to get a minus omega squared times b times sine of omega t times j. Right? And now we can factor out the omega squared. In fact, it's negative omega squared times what? Times a cosine of omega t I plus, right, because they're both negative, right, b times sine of omega t times j. Okay, so that's the acceleration. Okay, so we'll just call that a of t, right? Remember, acceleration is a vector. If you want the magnitude of the acceleration, just do the same thing we did for the speed, right? Take the magnitude of this vector, take the square root of the sum of the squares of the components, right? Okay. Oh, and we want to show that the acceleration vector points toward the center of the ellipse. Okay, so if we were to draw at a given point here, let's say right here, right, so the velocity vector will be something like this. But we want to show that the acceleration vector points toward the center. Right, so this will be the acceleration vector, and let's say the red vector is the velocity vector. So the velocity could be pointing anywhere, but the acceleration, they claim, points toward the center of the ellipse. Right. So just have to be a little bit clever here. Notice something about what's in the parentheses here. And I got to take you all the way to the beginning here. It just falls off there, right? What's a cosine omega ti plus b sine omega tj? It's this, right? It's way up here. It's the original position function, right? So this is really just equal to minus omega squared times the position function, right? So in this picture here, and I think I got to draw a bigger picture here. So here's the ellipse, right? Here's the center, right? We're at a given point, right? So here's my velocity vector. And let's say this is my position vector, again, at some given time. So notice that the acceleration will just be, since it's a negative, right? It points in the opposite direction, right? Times some constant. Now that constant might be, bigger than 1. And if it's bigger than 1, then it keeps going. So, if you say it points toward the center, you have to be careful. It looks like it points away from the center. But if you move the vector this way, then it points toward the center. So if omega squared is less than 1, then it points toward the center. So, right. So, and that's for any t. So as you move along the ellipse here, at a different time, the acceleration vector will change, but it will still point toward the center. Right? Right? And the position vector will also point away from the center. Right? And again, the velocity vector will point tangent to the ellipse, so something like this. Right? Approximately. Yep, so that's all you have to do. Recognize the thing in the parentheses as the original position function. And so the acceleration is just a constant times, right, times the position. And in fact, it's a negative constant, right? Omega squared, of course, has to be positive because it's the square of a number. So the negative sign really makes it a negative. And so that's why it's in the opposite direction of the position vector. Okay? Right, and that doesn't happen in general, right? In general, when you have a curve like this, right, curve C here, right, your position vector will be pointing this way. Let me do a better position vector here. How about this one here? So this is R, right? The velocity vector now the velocity has to point in a specific direction. It has to be tangent to the curve, okay? But then the acceleration vector, that could point any old direction here. Right? It doesn't have to point opposite to r. Right? It could. I mean, it does in this example here, of course, it does. But not in general. Right? Not in general. Now, if this is a curve in a plane, actually, even if this isn't a curve in the plane, it turns out the acceleration vector has to point in the plane of r and v, right? So let me draw a plane, right? If the curve is in the plane, let's say the curve is this curve here, right? And you have your position vector here at some point with the origin here. You have your usual velocity vector point. It's almost horizontal. It's almost this way, right? So that's your velocity. Right. The acceleration vector, right, has to point in some direction in the plane, right? It can't point outward like this, right? It has to point in the same plane. It has to be in the same plane as r and v. Okay. Now, we didn't show that, right? Why is that? I mean, intuitively, it should make sense, right? After all, if the acceleration were to point, let's say, directly upward, well, that at some time later, the velocity then would be pointing also away from the plane, not in the same direction as the plane. Right? So how can that happen? If the curve stays in the plane, the velocity implies, right, if the velocity is pointing away from the plane, then this object is going to be going out of the plane. It'll be up here instead of staying in the plane. And that doesn't happen, right? So intuitively, it does make sense that the acceleration vector also has to point, right, in some direction. It has to stay in the plane. And maybe this is a bad picture here, but the acceleration vector will also be in the same plane, say the plane P here. Okay. Right. So that's certainly true if the curve is in the plane. It turns out, even if the curve is a space curve like this, like a helix, it's also going to be true, but that's, you know, again, that's maybe not obvious. So we will actually get to this, I think, in the next video or two, in the next couple of sections, right? So still in chapter 12, I will actually show you that the acceleration has to be in the same plane as r and v. Okay. But anyway, that's you know, far removed from the answer, right? So the answer, we want the velocity, the speed, and the acceleration. And then to show that the acceleration points toward the center of the ellipse, just write it as a constant times the position vector, a negative constant times the position vector. And that does it, right? Okay, so I think that's it for this section. And the next section we'll talk more about, again, position vectors, but also the velocity and the acceleration, as well as something called tangent vectors and normal vectors. So that's in the next section.